Alright, so in example number 1, we're trying to find the area from 0 to 3 of 2x cubed using 6 rectangles. And I use 6 rectangles because it's easy for us to figure out that each one of these is 1/2. And so what I'm going to do is, I know that the base is 1/2 for the first one, and we're going to use the right side. And so if I do 2 times 0.5 cubed for the height, that will give me the area. And then I'm going to do 5 times 2 times 1 cubed and 0.5 times 2 times 1.5 cubed, and add up all of these areas until we get to 3. And so when I do this, I will start writing them down. So my first answer is 0.125. My second answer is 1. My third answer is 3.375. My fourth answer is 8. My fifth answer is 15.625. And my answer for 3 is 27. And when I add those up, I get an answer of 55.125. But I know that answer is too big because all of my rectangles are above the curve. So now I'm going to find the ones from the left-hand side. And so these 5 rectangles are the same ones that I used as the one before, except for now they're rectangle 2, rectangle 3, rectangle 4, rectangle 5, and rectangle 6. But my first rectangle is at the very bottom here, so my first rectangle has an area of 0. So when I add these 5 plus 0, the answer turned out to be 28.125. And this answer is too low, and this answer is too high, so we have to get the answer that's somewhere in the middle, and that's what the next example is going to be for. So when I do this, we'll think back to the old problem. In order to get the width of each of the rectangles, I did 3 divided by 6, which means this time I'm going to do 3 divided by n. Now I'm going to add up infinitely many triangles, which means that we're going to have the limit as n goes to infinity. And then I have to figure out what is each of the heights. Well, we plugged them into an equation that we had to cube, and for the first, and since I'm doing infinitely many, the left and the right doesn't matter anymore because they're the same place. I basically had to take my 2, which was not inside the parentheses, and then I had to take the first over n triangles, then the second, and then when I get to the last one, it will be n over n. So we have 3k over n to the third, where 3 is the length of the interval. So now I'm going to try and simplify this. On the bottom I have n to the 4th. On the top I have this 3, this 2, and 3 cubed becomes 27. So when I multiply 3 times 2 times 27, I get 162 k cubed over n to the 4th. all I'm really worried about is the summation of k cubed. So this 162 over n to the fourth can come on the outside. In the formulas I gave you today, k cubed is the same thing as n squared times n plus 1 squared over 4. And so when I multiply this out, I'm going to get 162 n to the fourth over 4n to the fourth. And as the limit as n goes to infinity, I wind up with 162 divided by 4, which turns out to be 40.5, which is in between the 28.125 and the 55.125 I got in the last problem. So let's see what changes when we do from 0 to 6. So we're going to still have k goes from 1 to n, limit as n goes to infinity, so that we'll have infinitely many. Now since my interval is 6, I'm going to have 6 over n, and then I'm going to put 2 something to the third into my equation, and this would be 6k over n. Because this time, each time I move, it's going to be 6k instead of 3k. So I'm going to try to simplify this up. So we got k equals from 1 to n as n goes to infinity. On the bottom I have this n and these three n's, so that's n to the fourth. On the top I got a 6, a 2, and 6 to the third power, and a k to the third power, so I just put the k to the third in there. So 6 times 2 times 6 to the third is 2,592. I'm going to take the 2,592 n to the fourth on the outside. And then I'm just going to be left with from 1 to n of k to the third power. Now, k to the third power in a summation is the same thing that I had on the last problem, which is n squared times n plus 1 squared over 4. If I were to multiply this out, the top would be 2592 n to the fourth plus other things divided by 4n to the fourth. Since we're doing the limit at infinity, I'm just going to do 2592 divided by 4, which is 648, which is my answer. So let's try this one more time with a different equation. So the question is now, what happens if we're going from 2 to 4? And also, what happens if we have this equation? Well, I'm going to set this equation up in a different way because we have 3 of them, so I can do this with 3 separate problems, and then we will just add the 3 answers together. So for the first one, so I'm just going to worry about the x squared part. I'm going to do from the summation from 1 to infinity of 2 over n. Now the reason why, because we have 2 over n, and we're going to use this for all of them, is because my interval is from 2 to 4. Now normally I would put just 2k over n, and square it, except for we're starting at a different place. We are starting at 2. So I have to put in that 2 at the very beginning. Now I'm going to do the summation from 1 to infinity. And maybe I should use a different for 4x. Well, we still have 2 over n. And we're going to use 4 times, so I put a little 4 on the outside, 2 plus 2k over n. And we have one more, which I will do, let's say, in green, where I have the summation. I'll move it back to the beginning here. From 1 to infinity of 2 over n, and then all I'm doing is plugging in whatever, and we only have 2, and so no matter what x value I put in, I'm going to get 2. And for all of this we have, I shouldn't have put infinity up here, I should have put n, because we're doing the limit as n goes to infinity. So let me quickly erase these and put down n. So let's try to simplify this part. So we have 2 over n times 4 plus, when you multiply this out, it will be 8k over n plus 4k squared over n squared plus the summation of, let's see, from 1 to n of 16 over n plus 16k over n squared plus the integral from 1 to n of 4 over n. From 1 to n of 8 over n plus 8k over n squared plus 8, I'm sorry, this should have been 16, because when we distribute the 2, that becomes 16k over n squared plus 8k squared over n squared. So I have this, and I have this, and I have this now that I'm trying to add together. So let's add the ones that have common denominators. So here I see 8 over n, here I see 4 over n, and here I see 16 over n. So that's going to be from 1 to n of 28 over n. So now we got 1 to n, and now I need to take care of, sorry, a quick little reminder that this should have been n cubed, because n times n squared is n cubed. So let's add the 16k over n squared here, and 16k over n squared here is 32k over n squared plus The only thing that we haven't used yet is this guy. So we got 8k squared over n cubed. Pull out anything that's not a k. So if I pulled everything else out, I'm left with 1. Over here, I'm left with k. And here I'm left with k squared. Now remember, we're doing the limit as n approaches infinity, but I'm going to plug in the formulas that I put on the board. So for 1, that's just going to be n, and those cancel, and so the first part just gives me 28. For the next part, my summation for k is n times n plus 1 over 2. And for this last one, we have n squared, which was n times n plus 1 times 2n plus 1 over 6. We're almost there. So here I got 32n squared over 2n squared plus stuff. And so this 28 needs to be added to, well, these two become a 16. And this one has an 8 and a 2 and 3n, so this will be a 16n cubed plus stuff divided by 6n cubed. So I'm going to add 8 thirds. And when I add 28 plus 16 plus 8 thirds, I will have my answer of 140 over 3. And that is section 13.5. If you have any questions, please feel free to ask.